Today in the workshop we'll be working with color sensors. I'll show you how to calibrate and use two popular color sensors with the Arduino. We're showing our true colors today, so welcome to the workshop. Hello and welcome to the workshop and to a very colorful episode of the DroneBot Workshop. Now, we've worked with color before in producing colors. We've had RGB LEDs and displays that can produce a variety of colors, but today we're going to be working with the opposite thing, and that would be sensing colors. Now, you could sense colors a number of different ways. A very simplistic way of doing it would be to use a light sensor and place a color filter in front of it so that only one color of light would be able to activate the sensor. A very sophisticated method of sensing color would be to use a video camera, where we're going for the middle ground today. We're going to look at a couple of dedicated color sensors and how we can use them with the Arduino. So before we do that, let's go and take a look at how color sensing works. So let's take a quick look at color sensors. Color sensors are used to distinguish color mixtures of red, blue, and green. They're used in industrial process and quality control. They're also useful in specialized lighting and photography applications. The outputs can be digital, analog, or variable frequency. Color sensors consist of arrays of photodiodes. There is a separate array for each of the primary colors. These arrays are addressed individually. The photodiodes used in color sensors have sensitivity that changes with color. Therefore, the output for each color is not linear. Color sensors do not provide an RGB value as an output. The sensors will require calibration in order to get an RGB value. Some color sensors can also sense infrared light. Now, the first color sensor that we're going to look at is a very inexpensive and commonly available module, and it actually goes by a couple of part numbers. The most common is TCS230, but it's also called the TCS230, and they're basically the same thing. Now, this is an older style of color sensor, and it's not the most accurate one, but if you calibrate it, it can still be useful. So let's go and take a look at that sensor right now. Let's examine the TCS230, also called the TCS3200. This is a color sensor array that has a variable frequency output. It operates with a voltage of 2.7 to 5.5 volts and provides a TTL output. The output frequency changes with the light intensity. It consists of arrays of selectable color phototransistors. There are 16 transistors in each of the color arrays. The sensor allows you to select the output frequency scale to match with your microcontroller or other output device. The module also has 4 white LEDs to illuminate the subject being sensed. The TCS230 is very inexpensive and quite commonly available. The sensor is available with or without a lens or light shield. The S0 and S1 inputs on the sensor determine the frequency scaling. The S2 and S3 inputs determine the photodiode selection. Here are the pinouts of the TCS230. On the left side we have the S0 input and the S1 input. These are the ones that determine frequency scaling. The output enable, which is generally not connected in most applications. And the ground. On the right side we have the S3 input and the S2 input. These are the ones that determine which color is being sensed. We have the TTL output. This is the variable frequency output, whose frequency varies with the intensity of the colored light. And we also have the VCC or power connection. So here's the TCS230 or TCS3200 sensor, and as you can see, this is a very simple module. It's got the sensor itself in the center, and you'll notice that it's got a clear top on it, and you can even look at it and see the actual color sensor in it if you look close enough. And it's surrounded by 4 white LEDs, and these are illuminated to light up the surface that you're actually sensing. Now on each edge of the sensor we've got a series of connectors, and these of course are the connectors that you're going to be using to connect it to your microcontroller, and they come out to DuPont pins that are on the back over here. So really not much more to say about this. It's a very simple device in terms of hooking it up, which is exactly what we're going to do right now. For this experiment, you'll require an Arduino Uno and a TCS230 or TCS3200 color sensor. We'll begin by connecting the 5-volt output of the Arduino to the VCC pin on the color sensor. We'll connect the Arduino's ground to the color sensor ground. Pin 4 of the Arduino will be connected to the S0 input on the sensor. Pin 5 will go to the S1 input. Pin 6 will be connected to pin S2, and pin 7 will be connected to the S3 input. Finally, pin 8 will be connected to the color sensor's output. And this completes the wiring. Now let's go and take a look at some of the code we'll need to use to run the sensor. So this is a sketch that we're going to use to calibrate our color sensor. We need to calibrate the sensor first before we can use it and get correct RGB values out of it. So we start off by defining the pins we've connected the sensor with. So the S0 through S3 are connected to pins 4, 5, 6, and 7 accordingly. And then the sensor output is connected to pin 8. Then we go and define 3 variables to measure the pulse width of red, green, and blue, because that's what we are going to be measuring to calibrate. And we'll initialize those as 0. Now in the setup, we set up S0 to S3 all as being outputs, and the sensor output is an input into the Arduino, so we set it accordingly. We're going to set the pulse width scaling to 20% because that means it will be in the range that the Arduino can easily measure. And then we will set up our serial monitor, which we're going to be using to display the results. I've set it up at 9600 baud. You can change that if you wish, just make sure your serial monitor matches. Now before we get into the loop, we'll go down and read one of the functions that actually reads the pulse width. So this is getRedPW. And we set the sensor to read the red only, in this case by setting S2 and S3 both low. And this is the only difference, by the way, between getRedPW, getGreenPW, and getBluePW. Otherwise, they're identical. We define an integer that represents the pulse width that we want to read, and then we read that pulse width with an Arduino pulse-in command. The low at the end of this means we're reading the amount of time that the pulse stays low. And we'll assign that to the value PW, which we return and exit the function. And the green and the blue ones are identical with the exception of setting the sensor values here to read green only or to read blue only. Now up in the loop, we are going to assign the values redPW to the value of the getRedPW function. We'll put in a slight delay to stabilize the sensor. Then we'll read the green, we'll do the same thing, and then read the blue. And then after that, we're just going to simply print our outputs out to the serial monitor. So this is quite a simple sketch, and it's going to allow us to calibrate the sensor. So let's go and do some calibration right now. Alright, well we're ready to calibrate our TCS230 sensor. So as you can see, I've got the sensor mounted facing down, and I've got a pen and paper here ready to take some calibration values. And I also have some color samples. Now these color samples are by no means professional. It's just some paper I picked up at the stationery store, so they're far from perfect. And also I want you to keep in mind that the ambient lighting in the workshop is going to affect this, the LED lighting. This will work better in the dark, but of course that wouldn't have made for a very interesting video. So here's my color samples. This, as you can see, is a white sample, and I've got a black sample, or as close to black and white as I can get. I've also got a red, which I personally think is closer to orange than red. I think my shirt is closer to red. I also think my meter probe is closer to red, but it's going to have to do. I've got a green, and I have a blue. And so we'll start off by placing the white sheet underneath the sensor, and we'll take a look at our serial monitor. Now you can see some of the values we're getting on the monitor right now. What we're looking for is the lowest possible value. And I've seen some values here down. I saw 41, I thought, earlier. Here's a 43. I'm going to put 43 because that seems to be about the lowest one we're getting right now for red. And for green, there was a 59 in there. 58. 58 seems to be the lowest value. And for blue, I saw 54. 48, there's a 48 there. There's another 48. Let's call that one 48. And now we're going to look for the highest values, and we will put the black under here. Now remember, this is not frequency, this is pulse width, so it's the inverse of frequency, so a larger number means a lower frequency. And we're looking for the highest number we can get right now. I saw 171, 172 over there. Let's call it 172. And for green, what's the highest that we're going to get? 246 just went by. I'm going to call her 246. And finally for the blue, 185 was up there, 184, 186. Let's call that 186. Okay, so now I've recorded the values of the lowest and highest values that I'm expecting to get for red, green, and blue, and I'm going to use that value in our next sketch, which is actually going to convert these to RGB values. Now this is a sketch that we'll be using to extract RGB values from the color sensor, and a lot of it is similar to the calibration sketch. It starts off identically by defining the pins that we've connected the color sensor to the Arduino with, and then we have to enter the calibration values that we received during our previous calibration experiment. And so you're going to need to replace all of these zeros with your actual calibration values. Now I'm going to do that right now, but bear in mind that my calibration values won't be the same as yours, so you really need to run the first sketch. Okay, the red min that I got was 43, and the red max that I received was 172. The minimum green pulse width was 58, and the maximum was 246. And finally for the blue, I had 48 as my minimum and 186 as my maximum. Okay, and again you'll want to modify that with your own calibration values. Now once again we set up the three variables to measure the pulse width for the three different colors. We also have some integers that represent the red, green, and blue values. These are our RGB values that we want to produce with the sketch. Now the setup is pretty well identical. We set the S0 through S3 as outputs. We set the sensor output as an input. We set our frequency scaling to 20%. And we are going to be using the serial monitor again at 9600 or whatever speed you would like. Just match that with your serial monitor. Now, we're going to use the same functions over here, the get red PW, get green PW, and get blue PW, so I won't go through them again because we've already done that. We'll go into the loop right now. And for the loop, we will read the red value with get red PW as we did before, only this time we're going to map it to a value of 0 to 255 to get the actual RGB value for the red. And so we're going to take red value and map that to the red pulse width with red min and red max, and notice that we're inverting it right now. So the minimum is going to go down to 255 and the maximum up to 0, and that's because we're talking about pulse width and not frequency, and pulse width is the inverse of frequency. And then the delay to stabilize the sensor. And we'll go through and do that for the green and the blue identically, and then we'll just print those values out to the serial monitor. So with the mapping, these should represent closely the red, green, and blue values, or RGB value, of the color that we're sensing. So now that we've looked at this sketch, let's go and give it a test. So now we're running our test sketch with the calibration values, and I've got the white under here. Now perfect white should be 3 values of 255, and we're not getting 3 values of 255, although we're coming very close to those values over here. So that's encouraging. And we'll put the black on under here, and of course a perfect black would have values of all 0. And again, it isn't all 0, but again, we're getting some very low values over there, so that does seem to be responding. And once again, these are not perfect black or white. Now I'll take the thing that I'm calling red, which, as I said, is not the reddest of reds. And what we should see is that the red should be the highest number. And indeed, that does seem to be the case over here, that the red is much higher than the green and the blue. And we'll take a green. And as we would expect, the green is the highest component that we're getting right now, higher than the red and the blue. And finally, we'll put a blue underneath here. And the blue is the highest. There's not very much red component, a little bit green component. And again, of course, these aren't perfect color samples, and the ambient light is affecting it. So as you can see, this is a color sensor that does work. It is not the most accurate one, but it can indeed distinguish between the different shades of red, green, and blue, and you could indeed use this for one of your projects. So as you've seen, the TCS230 is a usable color sensor, but it does leave a little bit to be desired. If you calibrate it correctly, though, you can certainly find a lot of use for it. Now, the next sensor we're going to look at is a little easier to use because it uses the I2C bus. It's the ISL29125 sensor, and I'm going to be using a module from Sparkfun, who have also provided libraries for using this device. So let's go and take a look at that color sensor now. Now we'll look at the ISL29125 module. This is an RGB color sensor module made by Sparkfun. The module uses an intersil ISL29125 RGB sensor with an integrated infrared filter. It has an internal analog to digital converter and light processor. The module communicates using 3.3 volt I2C. It also provides a programmable interrupt output. Here are the pinouts of the module. We have the ground pin, the 3.3 volt power supply, the I2C data or SDA line, the I2C clock or SCL line, and the interrupt output. You can see the RGB sensor in the center of the module. This module is not 5 volt tolerant. The module has internal pull-up resistors. If you wish to remove the pull-up resistors, you can cut the 2 traces illustrated here to disable them. The ISL29125 has internal registers that can be programmed to customize the device. These registers are used to program the function of the interrupt. The module provides a 16-bit data output. The I2C address of the module is fixed at hexadecimal 44. So now let's start using the ISL29125. So this is the Sparkfun ISL29125 module, and as you can see, it's a very basic module. It's got some connections on one side over here, and they are all labeled on both sides of the board. It's got the sensor right in the center, is really the meat of this whole thing. and it's a very, very tiny sensor, as you can see. On the other side of the board, there really isn't anything except these solder traces that you can cut if you want to not use the pull-up resistors. And so there you go, a very basic module that we will be using for our experiments. So let's see how we can hook this up to an Arduino now. Here's what you'll need for your experiments with the ISL29125. You'll need an Arduino Uno, a 2-channel logic level converter, and the ISL29125 RGB sensor. Optionally, you can also add 4 white LEDs and 4 dropping resistors for those LEDs. I used 330 ohms, but any value from 150 to 470 will work just fine. These LEDs are optional and are being used to illuminate the surface, and you can use an external light instead if you wish. We begin by connecting the 5 volts from the Arduino to the 5 volt on the logic converter. We'll connect the ground from the Arduino to the logic converter's ground, and the 3.3 volts from the Arduino to the 3.3 volt input on the logic converter. We'll also connect the 3.3 volts to the 3.3 volt input on the ISL29125. Next, we'll connect pin A4, which is the SDA, to one channel of the logic converter. That channel's output will be connected to the SDA input on the color sensor. Pin A5, or SCL, will be connected to the other channel on the logic converter, and its output will be connected to the SCL input on the ISL29125. We'll also connect the ground from the logic converter to the ISL29125's ground. If you're using the LEDs, connect one side of each resistor to the 5 volts from the Arduino. Connect the other side of that resistor to the anode on each of the LEDs. And then connect the cathode of all the LEDs to the ground. And this completes our wiring. Now, in order to work with the sensor, we're going to require a library that Sparkfun has kindly provided for the ISL29125. And you'll find a link to that library in the article accompanying this video. The library is available as a zip file, so you'll need to install that into your library manager. You can do that by going to Sketch, and then going into Include Library, and then Add Zip Library. This will open up a dialog box, and you should navigate to where you've downloaded your library, in my case my Downloads folder, and look for the library. This is it over here. Now you would hit OK to install it. I'm not going to do that because I've already installed it into my IDE. Once you've installed the library, there will be a couple of sample files, and we're going to run one of those files to start off with. So go down into File and go to Examples, and scroll down to the Examples for Custom Libraries section, and go down until you find the library, which is this one over here. Now you'll notice there are 3 sample codes that they provide for you: the basics, the interrupts, and the RGB LED. We're going to be running the basics, but I'll tell you what the other 2 do. The interrupts is an interesting sketch in which it creates an interrupt when a specific color has been detected, and this could be very useful in one of your applications if you want to trigger on the presence of a certain color. The RGB LED is also a very interesting sketch. What it does is it takes an RGB LED and it cycles it through the 3 colors, red, green, and blue. You shine this on the sensor and you look at the readings that you get on the sensor. In a way, it allows you to calibrate your sensor. We're going to calibrate it as well, but I'm going to be using the basic sketch. So let's just open that. Now this is actually a very simple sketch thanks to the use of the library. We start off by including the wire library, which is the library that's included in your Arduino IDE for working with I2C. Then we include the library that Sparkfun has provided for the sensor. We declare an object for that sensor and then move into our setup. We're going to be using the serial monitor, so we initialize it and note the baud rate that we're using, 115200. That's higher than you may have yours set, so make certain when you use your serial monitor, you set it to that baud rate. And then we go and initialize the sensor itself, which is just done with this init command, and we print to the serial monitor that it has been initialized. And now we go into the loop, and as you'll see, this is very simple code. We read the sensor values using the library, so we do a red read, read red, read green, and read blue, and assign it to 3 different integers. Now these are going to be 16-bit values, and not the 8-bit values that we've used with some other integers, and we're using an unsigned integer for that. And then we simply print those values out to the serial monitor. Now right now it is printing out in hexadecimal. I'm going to change this to decimal by writing DEC in over here, because I find that easier to work with, being a human who has 10 fingers and 10 toes. And so I'm going to change it to DEC, but you can leave it as hexadecimal. But I'm going to be using this sketch in order to calibrate my sensor in a similar fashion that I did with the TCS230. And so the decimal reading will be a bit more useful to me. But that's basically all there is to the sketch. Just load it up and run it and open your serial monitor, making certain to set the baud rate correctly, and you should see the results, which we're going to do right now. And here we have, ladies and gentlemen, a first in the DroneBot workshop, the upside-down solderless breadboard test. And I've mounted everything on the solderless breadboard, as you can see under here, and then mounted it in a similar fashion to the way that we tested the TCS230, so that I can perform essentially the same experiments. And I've got the serial monitor running. Now, in this particular case, we are not reading pulse width, we are actually reading light intensity. That is what the sensor is giving us. And the sensor is, of course, sensitive more in certain ranges of light than other ranges, which is why these aren't even. But I'm going to put the white piece of paper underneath it, and you can see the numbers that we're coming up with. Now keep in mind these are 16-bit numbers, so in theory we could go as high as 65,535 and as low as 0, but in practical purposes we'll never get to either of those extremes. Now let's try the black sheet of paper. And as you'll see, the readings are much, much lower. Now, you can use the exact same process we did with the last sensor to do a calibration between the white and the black and take the maximum and minimum ranges. And that is exactly what I am doing. Now, I'm not going to repeat that with this right now and write them down because you've already seen it before. But I will gather the numbers and I'll use them for the next sketch that we will use with this sensor. Now here's the sketch that I've created in order to use the ISL29125 to display RGB values. Now we're going to start off by including the wire library, the library for I2C, and then we'll include the Sparkfun library for the ISL29125. We'll create an object called RGB sensor to represent our sensor, and then we will enter our calibration values. Now I've entered the values that I obtained for the low and the high for red, green, and blue respectively, and I used the same method that I used for the TCS230. Now of course when you do this, you are going to want to change these values to the values that you obtain when you run the basic program from Sparkfun and get your values in decimal. Then we're going to also create some integers for the RGB values themselves, red val, green val, and blue val. We'll initialize those with values of 0. We're going to set up the serial communications as we did before. I kept the baud rate the same just because I don't want to go back and change my serial monitor. And we have the same initialization routine that we did before. We'll do a sensor init, and then we'll print that the initialization was successful. Now we go into the loop, and in the loop we will read the sensor values as we did in the basic sketch and assign them to integers called red, green, and blue. And again, these are 16-bit values. So now we're going to convert these values into RGB values, and we're going to do this in 2 steps. The actual conversion will use the map function, and you're now familiar with the map function. We'll take the red low and red high and convert them to values of 0 to 255. Now notice when you compare this to the previous sketch that we don't have to reverse them because we're getting color intensity values and not pulse width values like we did with the TCS230. Now after that, comes a command that you may not be familiar with, the constrain command. And the constrain command constrains the value of red, green, and blue to the range of 0 to 255. Now you might wonder, why do you need to do that? And the reason is that the map command, despite what you may think, can actually produce values lower than 0 and higher than 255 if we get values that are lower than the red low value or higher than red high. And this can happen with this sensor. The constrain command will constrain everything within the range of 0 to 255. So anything that goes below 0 will become a 0. Anything that goes above 255 will be 255. Now you might wonder why I didn't put all of these into the same command. Simply put constrain all around this statement over here. And the reason is you are not supposed to do that with the constrain command. You will get odd values if you do. You need to use this command separately. And you can see the link in the article accompanying this video to the article on the Arduino website that explains this command in great detail. After that, it's just a simple matter of going to the serial monitor and printing the red, green, and blue values and adding a delay for the sensor to stabilize, and then the loop repeats itself. So now let's go and take a look at our RGB displays from the ISL29125. Alright, so now let's test our sketch to display RGB values. So we have the serial monitor up, and we're going to bring our white piece of paper in. And this is our white sample, and yes, it looks very, very white. In fact, it's almost 255 all the way across, a little low on the blue side, and that's quite good. Now we'll substitute our black piece and see what we get here. And that's very, very black as well, too. It's pretty well down near the bottom, a 4, a 2, and a 1. Quite nice. And our red. And most definitely the red is the highest component in this. This seems to be a lot more positive values than we got with the previous sensor. Our green. And green is the highest value over here. The values seem to be staying pretty steady as well, too. And finally the blue. And it does seem to work on the blue as well. So this seems to give better RGB values than the TCS230 does. And I would say that if you're going to build a project with a color sensor, this would be the sensor to use. And so there you go, a couple of simple ways of adding color sensing to your application. Now, why would you want to use color sensing in the first place? Well, color sensing is used in a number of industrial and quality control applications, for example, grading fruits and vegetables. But if you don't want to grade fruits and vegetables, there's still a lot of things you can do with color sensing. You could, for example, make a special lock for your room and only let people with nice red shirts like myself into the room, or you could keep people with red shirts like myself out of the room if that's what you wanted to do. You could make, of course, a Rubik's Cube solver and sense all the different colored squares on the side of a Rubik's Cube. If you're a jelly bean connoisseur like myself, you will know that the black licorice flavored jelly beans are the best ones, and you could separate those out from the rest of the jelly beans, and I'm sure you can find a number of other interesting applications for color sensing. Now, if you want to discuss color sensing more, the best place to do that is on the DroneBot Workshop forum, where you'll find a lot of people just like you discussing color sensing, robotics, electronics, model railways, and all sorts of things. The forum is also the place to go if you would like to suggest new videos for the channel. Speaking of the channel, if you're not a subscriber yet, please do subscribe to the channel. Just hit the little subscribe button or the robot in the corner of this video and you will be subscribed. Make sure to hit the bell notification when you do subscribe, and that way you'll be alerted to whenever I make new videos. If you want to learn more about what's going on in the DroneBot Workshop, subscribe to the DroneBot Workshop newsletter. You'll find a link to that below this video, and you will also find a link to an article that accompanies this video if you'd like to learn more about the two color sensors that we talked about today. So until the next time we get together, please take care of yourselves, please go sense some color, and I will see you again very soon here in the DroneBot Workshop. Goodbye for now.